Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 12, 2026, just yesterday. It introduces a method called multi-head linear attention that restores the expressive power of standard models while remaining efficient, achieving a remarkable 41% improvement in video generation tasks. The paper is titled MHLA, Restoring Expressivity of Linear Attention via Token-Level Multi-Head. And as we'll see later, the results across image classification and language modeling are equally impressive. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, you can grab the MHLA 1.3 billion parameter models and find usage examples for tasks like video generation, language modeling, and image classification. Figure 1 illustrates these capabilities. Panel A displays high-quality generated images, proving the model handles fine details well. The charts in Panel B reveal a massive efficiency gap. While standard self-attention runs out of memory at high resolutions, multi-head linear attention maintains high throughput, running over 8 times faster. Finally, the radar chart in Panel C confirms that this speed preserves quality, with the method remaining competitive across language, video, and image benchmarks. Well, Figure 1 highlighted the performance, and now Figure 2 illustrates the mechanism behind it. The left panel depicts standard linear attention, which squeezes all token information into one global key value summary. While fast, this often loses critical details. The right panel introduces multi-head linear attention. Here, the model splits the sequence into blocks to form distinct local key value summaries. A multi-head mixing layer then dynamically blends these local summaries for each query, allowing the system to capture complex dependencies while maintaining linear speed. Alright, Figure 3 visualizes the global context collapse I mentioned, and how the new method fixes it. In Panel A, the matrices show standard linear attention is blurry, while multi-head linear attention recovers the sharp structure of softmax attention. The bird images confirm this. Linear attention scatters focus on background noise, but the new method locks onto the bird. Finally, Panel B quantifies the success. The rank, measuring representational power, jumps back up to match standard levels, while entropy drops, proving the model has regained its focus. So, while the previous figure demonstrated the restored expressivity, Figure 4 details the mechanism. In Panel A, the pipeline starts by dividing the input into blocks to generate local key value summaries. The core innovation is the learnable coefficient matrix shown in the center. This matrix mixes the local summaries for each query, allowing specific blocks to share information efficiently without scanning the entire image at once. On the right, Panel B visualizes this mixing behavior. The heat maps for Block 1 and Block 14 show that the coefficients favor neighboring regions initially, which helps preserve local details while maintaining global context. Okay, having seen the mechanism, Table 1 summarizes the theoretical trade-offs. The first row confirms that standard self-attention is powerful, offering a high rank bound and query condition selectivity, but it suffers from quadratic complexity, which limits scalability. In contrast, the second row shows that standard linear attention fixes the speed with linear complexity, but pays a heavy price. The rank is capped at D, and it loses that critical query conditioned ability. The bottom row reveals how multi-head linear attention solves this. It preserves the efficient linear time complexity while restoring the rank bound through the summation of block ranks, ensuring the model stays expressive without the computational cost. Alright, moving from theory to real-world performance, Table 2 reports the results on ImageNet classification. Panel A on the left compares attention mechanisms within the DIT architecture. Crucially, the proposed method reaches 75.8% accuracy in the tiny setting, beating standard self-attention while keeping the parameter count constant at 5.7 million. Then, looking at the state-of-the-art comparison in Panel B, the method scales effectively against strong baselines. In the bottom section, the larger MHLA VLTS model achieves 84.6% top 1 accuracy, outperforming recent efficient models like Versus Mamba. Wrapping up, 2 takeaways stand out. First, multi-head linear attention successfully bridges the gap between linear efficiency and softmax quality by fixing global context collapse. Second, its consistent gains across video, image, and text tasks suggest it could become a standard for future high-resolution generative models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.